So thank you everyone for coming in this morning. This is actually one of the harder lectures of the semester, I think, so I'm glad you're all here. I will record this and put it up on YouTube as usual. I'll put the link online. I do need to remind you that Thursday, 1 week from today, we're going to have our third exam. So we'll cover chapter 7, which I think this is probably the hardest exam of the semester, so you need to practice these a lot. Really what these take is practice more than anything. Once you do these a lot, there's stuff that are undoable. They just need you to try them a while before you get them. So I've already put up a set of practice problems online. Don't let them scare you. It's longer than the actual test is going to be, but the actual test will be the same sort of flavor, just like the first two exams. So try practice exam 3 on D2L with all the other handouts for the semester. Most of the problems on the exam are going to be similar to that. If you can do problems similar to those on the exam, you'll probably pass, almost surely. Some of the problems will not be like that. They'll be based on homework problems that I didn't put on here. These are the most important problems. That's why I put them out for you to study. All problems similar to homework. So it's the same style of the whole first two exams. So to get an A on the test, you want to go through and make sure you can do all the homework problems, right, out of this chapter. Like the previous exams, it's by email only. Don't come to class that day. You'll sit here by yourself. You missed the exam. Next time, we're going to spend most of the period reviewing. So try these problems out, practice problems especially, but all the homework problems. Bring whatever questions you have to class, and we'll answer the questions on Tuesday. Come by my office hour too. Hardly anybody's coming, so you probably get a lot of time to talk to me. I write things on the board and put them online. And if you can't make those, I do schedule other hours. People are scheduling other hours to meet me. I can even meet in the evening since it's by WebEx, right? Tuesday review for the exam. Any questions on the exam? All right, so look at all these problems then. The last ones will be for today. I'll go ahead and put the new homework. It's section 7.5. We did the first half of this section last time. We said we're spending the whole week on this because this is one of the hardest sections of the book. 7.5, just do all of the problems on the supplement. All UCO homework supplement problems. Some of these, honestly, are similar to the previous ones. If you got the previous one and say, oh, bad again, then okay, skip it. But make sure you can do them all is the idea. Let's get going on today then. This one warrants a little bit of review because the techniques are a little difficult. The topic was solving trigonometric equations. And we said we could do this in steps. And the first step was to be able to solve trig function of theta equals a number. The book will write as trig function of x equals a number, same thing with a different letter. I like to reserve x so I can draw it on the unit circle and draw theta as an angle. So I'm going to suggest that when you do the homework problems, put theta in there to keep track of what's the angle also, but certainly leave it x like the homework set does if you want. I think the homework set is just trying to follow the book. I suppose we want to solve trig function of theta equal to a number. Put all on the screen there, I hope. Yeah. And we said, let's just do this by an example. This was the hardest case. We did these last time, but I'm going to do some of the harder cases here. Suppose I want to solve and the method is just simply to appeal to the unit circle. As follows. For instance, suppose I want to solve tangent theta equals 1 over square root 3, right? What do I do with that? Well, you first say, remember, tangent theta is the hard case. If it's sine or cosine, then you say, oh, it's the x or y coordinate. I just put those two, I put the x or y coordinate equal to this number. I can solve it on the unit circle. But tangent is the hard case. We say tangent is defined to be y over x on the unit circle. And now I can't interpret this as y and this as x because it's not on the unit circle. This one's 1.732 approximately. It's already outside the unit circle. So I have to write this as a point on the unit circle, and I recognize if I just divide these by 2, 1/2 square root 3 over 2 is a point on the unit circle, right? Just by memory, if you like. That's the easiest way to do it, is remember. But if you don't remember, you can always make a quotient into a ratio of points on the unit circle by dividing through by the root sum square of these two numbers. So I'm going to divide through by 1 squared plus square root 3 squared, right? Root sum square of these two numbers is square root 4 is 2. That's what I have to divide by to make a point on the unit circle. Then there's a second point on here. If you were to take minus this number over minus the other one, it would have the same ratio. And these are the only 2 points on the unit circle that have this ratio, 1 to square root 3. That's it. So you can interpret this as y and this is x, or you can interpret this as y and this is x. This looks familiar, hopefully. I'm doing it a little faster this time. And that's the only points in the unit circle. So I draw the unit circle. That's the strategy, right? Put the x and y coordinates on it. I can have y equals 1/2. Since it's a unit circle, it's halfway to the top. X equals square root 3 over 2. That's about 0.8 something, so it's way out here. And we have that point on the unit circle. We put a terminal ray through there. That's possible. Or we can have y equals -1/2. X equals minus square root 3 over 2. And it's always directly opposite, right? Here's -1/2 minus square root 3 over 2. And those are the only 2 points with the correct ratio. That means there's exactly 2 terminal rays that can have this, that can correspond to this tangent. Wonder what the angles are that they're at. To do that, I drop a perpendicular, we said, to the x-axis always, it's convention. Complete the right triangle using the segment out to the point and the segment along the x-axis. Then this would be one angle that goes to a terminal ray. What angle is it? It's easy, right? Since I go from 0 up to 1/2 here, this side length must be 1/2. Since it's a unit circle, this side length must be 1. Also, this goes 0 to square root 3 over 2. This side length must be square root 3 over 2. And similarly, this triangle over here is always congruent. You can see it by the symmetry of the situation. Square root 3 over 2, 1/2, 1. We memorize that triangle. That makes this a 30-degree angle, or pi over 6 radians. That's one solution, right? Solutions are all angles that go to either of these 2 terminal rays. This angle, by the fact that these are congruent triangles, is also pi over 6. And so the angle all the way around is pi, the straight angle, plus pi over 6 makes 7 pi over 6, right? 6 pi over 6 is pi, plus pi over 6 is 7 pi over 6. So we have 2 solutions within within one rotation. Theta equals pi over 6, or don't write n, that means it has to satisfy both equations. There it is. If the problem says for theta between 0, solve this for theta between 0 and 2 pi, these are the only answers. You start here, rotate around to the first ray. Oh, that's pi over 6. Rotate around to the second ray. That's 7 pi over 6. That's it. Those are the only 2 terminal rays within one rotation. Now, if the problem instead doesn't say anything, just solve y over x equals tangent theta, then I have to find all angles that go to these terminal rays. What are all angles that go to these terminal rays? They're all the coterminal angles, right? They share the terminal rays, they're coterminal. Those are these plus any whole rotations, plus or minus. 2 pi times an integer. 2k pi is the convention for writing it. Where recall k can be any integer, 0, 1, -1, 2, -2, and on forever. The integers are numbers with nothing after the decimal point, so these are whole rotations, counterclockwise or clockwise, right? What do we multiply by 2 pi? There's all the answers. You don't have to write this. People assume it when you write k instead of x, right? Any questions on that one? That was the hardest one of this group. So we're still reviewing a little here. Suppose I said this time solve secant theta equals minus the square root of 2, right? How do we solve that one? We said if it was a secant or a cosecant, we immediately wrote the reciprocal equation, cosine, in this case, equals -1 over square root of 2. So if these are equal, then their reciprocals are equal. We can solve this equation instead of this one, and this is easy because cosine theta, recall, is the x-coordinate on the unit circle. So we draw the unit circle and we draw the line of all x coordinates -1 over square root of 2. This is about -0.7 something. Look out here.
You might want to move.
Yeah, you're right. Thank you. Yeah, I'm sorry, I forgot. Oops.
Yep, that's good.
Okay. So here's, if I want to solve secant theta equals a number, I write the reciprocal. The reciprocal cosine is the x coordinate. So here's all points in the plane with x coordinate -1 over square root of 2. This is the line x equals -1 over square root of 2, right? Since it cuts the circle, it intersects in 2 places, which means there's exactly 2 possible terminal rays. Now, when we drop a perpendicular to make a reference triangle, as we call it, these 2 triangles are congruent. We notice that since we go from 0 to -1 over square root of 2, the length of the side is +1 over square root of 2, also known by rationalizing, multiplying by top and bottom by square root of 2. This is square root of 2 over 2. Now I recognize the unit circle. If this is 1, and this is square root of 2 over 2, then this side is also square root of 2 over 2 by memorization of the special triangles, and this side too. This must be a 45-degree angle, pi over 4 radians. And this also. Which means, so once again, if I want all angles from 0 to 2 pi, I start here, rotate around to this one, and I say, oh, it's pi back up pi over 4. Which is 1 minus a fourth is 3/4 of pi, right? 1 pi minus 1/4 pi is 3/4 pi. The other one is pi plus pi over 4. Gives me 1 pi plus 1/4 pi is 5/4 pi. Those are the 2 angles between 0 and 2 pi. Let's just do that this way. Let's say 4 theta in this interval 0, 2 pi, which means, this is notation, means 0 less than or equal to theta, strictly less than 2 pi. The round bracket means don't include the endpoint, the square bracket means 2. So these will be all solutions if you want in one rotation. If you want solutions arbitrary, any real number, then you'd have to add 2k pi to each of these like we did. So that was the first step, just to remind you of what we were doing. Then we said we might have a multiple of an angle, right? We might have this kind of situation. When you solve Trig function of a multiple of theta, say k theta equals a number. It's an easy step, right? Just set your favorite letter, such as phi, equal to k theta, solve by step one, this time for phi. Then put back k theta for phi and solve for theta. If you're restricted to the interval 0 to 2 pi, then you have to eliminate solutions not in 0 to 2 pi. Okay. So for example, I might say, solve sine of 2 theta equals minus a half. How about that one? Trig function of k theta equals a number, where k is 2 in this case. What you do is just replace this with phi, or whatever your favorite letter is, and solve sine phi equals minus a half on the unit circle, saying sine is the x coordinate on the unit circle. So, I'm sorry, y coordinate in the circle. So minus a half is halfway to the bottom of the unit circle, right? The horizontal line is all coordinates y equals a number. Right? So here's the line of all y coordinates minus a half, going through this minus a half on the y-axis. It intersects the circle in exactly 2 points, so there's exactly 2 possible terminal rays. What are the angles that go to those? Let's do this, solve this for the harder case. Theta between 0 and 2 pi, one rotation. If I want to solve it for theta between 0 and 2 pi, I first solve it for phi between 0 and 2 pi. And say there's an angle here. And what angle is it? Well, we drop the perpendicular, make the special triangle, and say, well, it goes down half a unit, so this side is a half. It's a unit circle, this side is 1. There's only one triangle, it can be by the Pythagorean theorem. This side will have to be square root of 3 over 2. This must be a pi over 6 angle. And correspondingly, this one also. They're always congruent triangles here. So I have 2 angles. Pi plus pi over 6 is phi equals 7 pi over 6. And 2 pi back up pi over 6. Well, 2 pi is 12 pi over 6, right? Take away pi over 6 makes 11 pi over 6. So 7 pi over 6 and 11 pi over 6 are the angles phi within one rotation. But when you're restricted to one rotation like this for the problem, trig function of k theta equals a number, I say still find all solutions and then throw out the ones you don't want afterwards. And here's why. If I just take these two, I would say, oh, 2 theta equals this, it must be theta is 7 pi over 12. 2 theta equals this, it must be that theta can be 11 pi over 12. 2 solutions. Wrong, right? You want to be able to find all the solutions in 0 to pi. That's not all. Because all solutions here are this plus any whole rotations, right? All angles leading to this terminal ray are the coterminal angles, this one plus 2k pi. All of this one are this angle plus 2k pi. And now I have all solutions here, and I find those first, and let's see what happens when I find all solutions and throw out the extras. All right. I divide this by 2, getting theta on the left equivalently. So equivalent to these two solutions. If I divide the left by 2, I have to divide both terms. Terms are things that are added together. Right? Factors are things that are multiplied together. Terms are things that are added together. I divide each term by 2. So 7 pi over 12 divides that one by 2. 2k pi over 2, the 2's cancel, and you get k pi. There's the right side divided by 2. This one, I divide both sides by 2, I get theta equals 11 pi over 12 plus k pi. So these are all solutions, theta. But now we want to restrict to 0 to 2 pi. We try the different k values. So the solutions theta between 0 and 2 pi, I try k equals 0 here, start near 0. 7 pi over 12 plus 0 pi is just 7 pi over 12. That's between 0 and 2 pi, because 2 pi is 2 pi times 6 over 6, right? Is 12 pi over 6. This is less than 12 pi over 6, so that's a solution. Now I try k equals 1, comes from k equals 0 in the first equation. I try k equals 1. Then I get pi plus 7 pi over 12. Well, that makes 13 pi over 12 if you think about it, right? Pi, 1 pi is 6 pi over 12, is 12 pi over 12. 1 second. So pi is 12 pi over 12 plus 7 pi over 12, that does work. So I get, when k equals 1, 7 pi over 12 plus 1 pi is 12 pi over 12 is 7 plus 12 is 19 pi over 12. I get that from k equals 1. Is that between 0 and 2 pi? Sure it is. 2 pi. It's not, is it? So that's a. Oh, I suppose I wrote 6 here. Yeah, so 2 pi, I should have done this times 12 over 12 is 24 pi over 12. So I need angles between 0 and 24 pi over 12, and this is, right? So these two are between 0 and 2 pi. And then I try k equals 2. Well, k equals 2 fails because then I get 2 pi plus a positive angle is bigger than 2 pi. So k equals 2 is not good. So these are notes here. I'm just doing these on the side. K equals 1 is obvious. So I just add 0 and I get 7 pi over 12. And k equals 0. K equals 1, I get this angle. K equals 2, I get 2 pi plus something is too big. If I put k equals minus 1, I get minus pi plus 7 pi over 12, that's going to give me a negative angle. That's too small. So only k equals 0 and k equals 1 in this first equation. Give me angles between 0 and 2 pi. Now I try the second equation. In the second equation, if I put k equals 0, I get 11 pi over 12, and that's okay. That's 12. That's okay. That's between 0 and 2 pi. So I'll put 11 pi over 12. Then I'll put k equals 1, and k equals 1 I have to compute. 11 pi over 12 plus 1 pi is 11 pi over 12 plus 12 pi over 12. 11 and 12 is 13 pi over 12 times pi. I'm sorry, 23 pi over 12. So this is going to be 23 pi over 12. That's less than the 24 pi over 12 is 2 pi, so it's okay also. We take all angles from 0 to 24 pi over 12, which is 2 pi. Now if we put k equal 2, then we've got 2 pi plus a positive angle. Don't even compute it, right? It's bigger than 2 pi. 2 pi plus a positive is bigger than 2 pi. If I put k equals minus 1, then this is minus 12 pi over 12 added to this one is a negative angle. K negative doesn't work. So in this one, once again, k equals 0 and k equals 1 give us the 2 angles. Depending on which angles you picked here, you might need a different value of k. But instead of using 11 pi over 12 here, I would have been adding to minus pi over 12. I don't know if you can see it all online. But you might have to pick different values of k, but by trying all values of k, you come up with all solutions. And now, aren't we glad we didn't restrict phi to be between 0 and 2 pi and get only 2 solutions? There are 4 solutions. We found all solutions throughout the x's. Why did we find 4 here? Well, when we restricted to 0 to 2 pi over here, we only found 2, right? Reason is we can't restrict phi from 0 to 2 pi. It's equal to 2 theta. If theta is stuck between 0 and 2 pi, phi we have to consider twice that big, goes from 0 to 4 pi. So we can omit this step here of throwing out the extras if we let phi go from 0 to 4 pi and take all theta. But it's complicated to remember. I just say I prefer just to find all the angles theta and then throw out the extra ones. So do it whichever way you like. Find phi between 0 and 4 pi and find all corresponding theta, or find all theta and throw out the extras. Questions on that one? That's kind of getting difficult. And we remind step 3 was if you have a linear equation in a trig function, this is a little step again. Remember, a linear equation in algebra in one variable x is ax plus b equals 0. This is called a linear equation if it can be put into this form. Sometimes they'll write it this way, and you subtract c over and put it in the other form. All linear equations are the linear equations that can be put in this form, right? So a linear equation, this is a linear equation in x. So a linear equation in a trig function is the number a times a trig function, plus b equals 0. How do you solve it? You just solve it by putting x equal to trig function and solving for x. Or you don't even have to put it in, just solve for the trig function. And go to step 1. Once you have solved for the trig function, you have trig function equals a number. Step 1 or 2, depending on whether it's an angle or a multiple of an angle. So here's the example. Well, as I said, solve for all theta, not just 0 to 2 pi. On the test, if I say 0 to 2 pi, then you restrict, but if I say nothing, then you find all angles. You have to put that plus 2k plan in. Solve for all angles theta. Let me move this over because I'm running out of room. The equation 2 times cosine theta plus 1 equals 0. What if I have that one? You recognize it's just an a times trig function plus b equals 0. What you do is simply solve for the trig function by subtracting 1. This is an easy problem in algebra. It's ax plus b equals 0. You subtract 1 and divide by 2, and you have x, right? So I subtract 1 and divide by 2, and I have cosine theta. Cosine theta equals minus 1/2. Now it's just like step 1. Right? Go to 1. Trig function equals a number I solve on the unit circle. Cosine is the x coordinate. So I need x equals minus 1/2, halfway to the radius of the circle over here. X equals a number is a vertical line. That leaves 2 points in the circle of intersection, exactly 2 terminal rays. I just have to find the angles there. If I complete the reference triangles, I know that this is going to x equals minus 1/2, so the length of the side must be plus 1/2. It's a unit circle, so this side is 1, the last side must be square root of 3 over 2, as a Pythagorean theorem or memorization. That means that this is a pi over 3 or 60-degree angle. Same with this one, they're always congruent. That means theta can be this angle. What is it? Pi back up pi over 3 is 2 pi over 3, right? 1 pi minus a third pi is 2/3 pi. How about this one? Pi plus a third pi. Pi is 3/3 pi plus 1 more third pi is 4/3 pi. There it is. Theta equals 2/3 pi or 4/3 pi. If you're asked for all angles within one rotation, you start here, go around, that's that one, 2/3 pi. Go all around here, that's that one, 4/3 pi. That's all you have within one rotation. Terminal. If you want all angles, you add 2k pi to each of these. That's, we didn't write anything here, so we assume we want all angles. All right, that's what they said, solve for all theta. So it's plus 2k pi to get all angles. You can put a comma or the word or in the same thing. Questions on that one? They're getting harder and harder. All right, now step 4 that we did briefly last time was a quadratic equation in a trig function. Now we said that in algebra, a quadratic equation in x was ax squared plus bx plus c equals 0. So what's a quadratic equation in a trig function? It's just replacing x by a trig function. So from the quadratic equation in x, the quadratic equation in a trig function is a times trig function squared, any number a at all, not equal to 0 or it's not a quadratic, plus b times the same trig function, because it's supposed to be x again, plus c equals 0. There's a quadratic equation in a trig function. See a trig function squared and a trig function of the first power, think quadratic equation. How you solve this one is you substitute x equals the trig function to get a quadratic equation, right? This one, ax squared plus bx plus c equals 0. We know how to solve that 2 ways, right? 3 technically, but the third one doesn't bring anything new into the game. So here's how you solve a quadratic equation of trig function. A, substitute x equal the trig function to get a quadratic equation. B, solve the quadratic equation for x. How do you solve a quadratic equation? One way is factor, right? Often you can factor it when you can, that's fastest usually. Or another way is the quadratic formula. That always works. Sometimes it's difficult to factor. I highly recommend you memorize this. You'll need it in calculus if you ever take that. It's x equals, we wrote it last time, minus b plus or minus square root b squared minus 4ac. Did I say that for the test, it's open book, open notes, open computer, just like before? But no person can help you, no collaborating, no talking to other students during the test, no online tutors kind of stuff. I had one problem with that already this semester. I don't want to do it again. But all right. So here it is, minus b plus or minus square root b squared minus 4ac all over 2a is always the solutions. If you get a square root of a negative here, what does that mean? Now I'm stuck, right? No, it means there's no solution. If you get a square root of a negative, it means there's no real number solutions. Just imaginary numbers. We don't do those in this class. So No real solutions. If b squared minus 4ac is equal to 0, remember from algebra, you get plus or minus square root 0. They're the same solution. There's only one solution. Plus or minus 0 is minus b over 2a is the one solution. If b squared minus 4ac is positive, then you get plus the square root and minus the square root is two different solutions. So you can get 0 solutions, one solution, or two. But you find the solutions, and now what you have, x equals one or two numbers, or 0. Now, go to step 1 or 2. Because you now got trig function equals a number. Because you have the trig function equals x equals this number. Trig function equals a number, step 1 or 2. That's it. I'm going to put one more step in addition, just to mention what happens if you don't get a special angle. But in some sense, it's all these 4 steps. There's how to solve these. And now we're going to do the rest of the period, some more difficult problems here. We did one of these last time. Here's a different case. Suppose I want to solve here we go, 6b. The sine squared plus 2 sine plus 1 equals 0. How can I solve that one? When you see the sine squared and the sine in there, think, oh, it's a quadratic equation. Think of 1 times sine squared is a times sine squared plus b times sine plus c equals 0. If I put x equals sine theta, this immediately rewrites as ax squared plus 1x squared plus 2x plus 1 equals 0, a quadratic equation. I know how to solve a quadratic equation. I can factor, I can apply the quadratic formula. Maybe I could try factoring. Remember the factoring game? Blank x plus blank x plus blank. Something goes in the blanks. The product of these two has to be the coefficient of x squared, 1, because this times this is the only thing you get when you FOIL. That's x squared. So this times this, we need 1's in here to get 1x squared. Or you put minus 1's, but then you factor those out and cancel them so it doesn't do anything new. So these are 1's. Now what goes in these blanks? This times this is the only thing that gives you a constant term. So this one, the product is 1 to match the lead coefficient. This one, the product is also 1 to match the constant term. Well, let's try then minus 1 and minus 1. Their product is 1, right? You put these things in that will work and you try them. You FOIL it. This time this is x squared. That's right. This time this is minus x, and this time this is minus another x is minus 2x. And then this time this is 1 like we wanted. It's all right, except we got minus 2x instead of plus 2x. What's wrong? We should have put in plus 1 and plus 1.
Yeah, that's right.
Yeah, these also have product 1. And now I'll try foiling. So you try different things that whose product is 1 and product is 1 until you get one that gets the right middle term. Now, this time this is x squared. This time this is x. This time this is x. There's 2x. Oh, good. This time this is 1. Now it checks it by FOIL. So if I write this brevity here, it's x plus 1 times x plus 1 equals 0. Now the 0 product property applies, we said, right? If a product, this times this is 0, then at least one of these two factors are things that are multiplied together, is 0. Either x plus 1 equals 0 from this one, or x plus 1 equals 0 from this one, or both. But at least one of the factors has to be 0 in order for a product to be 0. The only solution out of this is x equals minus 1. Ah, there we go, because x is sine theta. So this equation here is equivalent to sine theta equals negative 1. Trig function equals a number. Now I go to step 1. In step one, solving trig function equal to number, I just draw the unit circle. Sine is the y coordinate. I kind of hate that I wrote x here, but I made that substitution. Sine is the y coordinate on the unit circle. So it's y coordinate equal -1 when I plot it here. Is just tangent to the unit circle, right? So there's only one point on the unit circle that satisfies sine theta equals -1. And that means there's only one terminal angle, terminal ray possible. It's this one. Which means there's only one angle between 0 and 2 pi, right? If you rotate it all the way around, it's just one, there's one terminal ray. Right? It's pi over 2 plus pi over 2 plus pi over 2 is 3 pi over 2. Or you could say 2 pi back up pi over 2 is 3 pi over 2 way. So from that diagram, we infer then, if sine theta is going to be -1, then theta has to be 3 pi over 2 if it's going to be within rotation. But we didn't specify rotations here, so we assume we want all solutions. We need to add all terminal rays, 2k pi. There's all solutions for this quadratic equation. Only one in this case. Within one rotation, but an infinite number overall. Now it gets sticky. Here's the next example. I think these are good examples here. I'm going to try to do a lot of these. This would be 6D. So when you do the homework, we'll have some of these written down for you. Suppose I had sine squared. I'm going to write it a little differently, though. Sine squared theta minus 2 sine theta minus 4 equals. What could this one be? Well, again, put x equals sine theta to recognize a quadratic equation. X squared minus 2x minus 4 equals 0. This is a quadratic equation x. This one was a quadratic equation in sine theta. Now I might go to factoring again. I might say, oh, blank x plus blank x plus blank. I'll just do the same thing I did before. And often that works, but I don't see anything that goes with these blanks right away. To get the 1 up here, I need 1 and 1 here. Now this product has to be -4. So I can put -4 and 1. And let's see, I got x squared plus x minus 4x is minus 3x, not minus 2x, plus this one's minus 4. That doesn't work. Well, I can switch these and put plus 4 and minus 1. Now I got x squared minus x plus 4x is plus 3x minus 4. Why can't I get that middle term to match? The answer is that factoring is not always easy. That's why we have the quadratic formula. This is a difficult guessing game sometimes. When you see it immediately like that, write it. It's faster. When you don't see it immediately, go to the quadratic formula. You're getting to relearn some algebra this semester. We know always the solutions are minus b plus or minus square root b squared minus 4ac all over 2a, right? We know that. You get this by solving it using the third method. We didn't put up completing the square. We didn't put it up because completing the square just leads to the quadratic formula. It's the formula for completing the square. So we don't need the formula and the method. All right. Minus b is b, here's c, including the minus sign, right? And a. So it's minus b is plus 2, plus or minus square root, minus 2 squared, minus 4 times 1 times -4. All over 2a is 2. So let's see, it's 2 plus or minus square root of 4 plus 16 is 20. All over 2, and we can simplify that. Those are just class of hone your algebra skills, right? How can we simplify that? Remember when you have a square root of a number that has a square in it, you can reduce it. Think of 20 as 4 times 5. 4 is a square, I can reduce this. Right? This is still on the screen, right?
No.
Oh, yeah, thank you, I was just looking, thanks, yeah. Okay, so here we have 2 plus or minus square root of 20 over 2. We rewrite this, square root 20 can be rewritten as square root 4 times 5, and the square root of the product of positive numbers is the product of the square roots, is 2 square root 5 in this case. So I'll rewrite this as 2 plus or minus 2 square root 5 over 2. And now maybe I'd just like to cancel these 2's. Can I do that? Trick question. No. It doesn't work. You can't cancel terms, things that are added together. You can only cancel factors. Something that multiplies the whole top can be canceled with something that multiplies the whole bottom. So I can't do that. I see people do that in the test a lot, is why I wrote this down. It's a common mistake. What you do is you factor 2 out of the top. You see there's a 2 in everything. So you put 2 times 1 plus or minus square root 5, right? That factors the top, pulls the 2 out. 2 times this is 2. 2 times this is the 2 square root 5. Over at the bottom, you can think of as 2 times 1, right? 2 multiplies the whole top, 2 multiplies the whole bottom, and cancel now. That's what it is. This whole thing is just 1 plus or minus square root 5. That's a lot easier than this. I want you to write this, not this, right? Okay, moving on over. This is x, but x was sine theta. So we have actually 2 possibilities. Sine theta equals 1 plus.
Okay.
Is it okay? Is it off?
Just forgot I had that silly thing on.
Sorry, I'm not catching something there. Sometimes the speaker isn't so good. This is sine theta equals this, so I got sine theta equals 1 plus square root of 5 or sine theta. I'm driving this board. Sine theta equals 1 minus square root of 5. These are both solutions by the quadratic formula, right? One for the plus, one for the minus. This is the case where the quadratic formula tells us there's 2 solutions to the quadratic equation here. All right, now I try and solve both of these. Am I going to be able to solve this one? No, why not? Square root of 4 is 2. Square root of 9 is 3. So square root of 5 being between 4 and 9 is between 2 and 3. It's 2 point something, right? 1 plus 2 point something is bigger than 1. There is no solution. Remember, right, the sine theta looks like this. It wanders up and down between plus and minus 1. It's never equal to a number bigger than 1 or less than minus 1. So this has no solution. Sine theta equals number bigger than 1. It isn't, right? Only goes up to 1. So there's no solution. I'll put empty set for that one. Or sine theta equals 1 minus square root of 5. Again, this is 2 point something. 1 minus 2 point something is less than negative 1. Well, it's never less than negative 1 either. So this is also the empty set. There are no solutions to this problem. How about that? So that's how you prove it. You show the only possibilities are sine equal a number bigger than 1 or sine equal a number less than negative 1. No solution. Well, I'll put this as one last step, although sort of it's the other ones. But we'll just say this: if in step 1 or 2, we have trig function equals a number that doesn't come from a special angle. So if theta is not a special angle, multiple of 30 or 45 degrees, then you can still find the solutions exactly in terms of the inverse trig functions. And we'll do that by example. Plus some multiples of pi sometimes. But I should say in terms of. Then the answer, and if you're on your card, and it's no good for somebody to say, well, it's the arctangent of 17. Well, what angle do I measure? Right? So you also sometimes want to get the decimal equivalent. The decimal equivalent is found in the calculator. So some of the problems will say, find the exact answer, even though it's not a special angle. Others will say, find the answer and round, so you can actually go out and measure it when you're doing it to, build something. All right, so these can be rounded on the calculator. Not exact. So that's the last and final step. You leave that sit there a little bit in case you're writing the last part of that. Here's the kind of fun problems you can get. Now, this would be 7b. Solve exactly on the interval 0 to 2 pi. So it means theta between 0 and 2 pi not equal to 2 pi. The following, not 7b, I'm on 7c, I'm sorry, 7c, is sine 2x minus sine x equals 0. How in the world do I solve that one? Here's the problem. It's not a linear equation, sine x. A sine x plus b equals 0. It's not a quadratic equation. A sine squared plus b sine plus c equals 0. It's got sine x and it's got sine 2x. It's got two different angles. What am I going to do with that? None of my techniques apply. The object here is to convert it into one of those other cases. So convert by using an identity. If you have a double angle, that suggests I use the double angle identity. This is why it takes practice. You do these till you recognize, I know how to make this into one of those other cases. You have to do it to memorize the other cases and then try a few of these converting it. Sine 2x is 2 sine x cosine x, right? So I'll write this equivalently as 2 sine x cosine x minus sine x equals 0. This is a real tricky problem here, right? And it's still not one of those cases. What can I do? Factoring to the rescue. So factor, we notice there's a common factor of sine in both of these. Back to the left side, that is, as sine x multiplies 2 cosine x and minus 1. This times this gives me this term. This times this gives me this term. Now I've got it. Zero product property. If the product's zero, then at least one of the factors is zero. This is equivalently either sine x equals zero or 2 cosine x minus 1 equals zero. One of the factors has to be zero. Now this is equivalently sine x equals zero or cosine x. This is a linear equation, right? This is method 3. Linear equation, you add 1 and divide by 2 and get cosine x equals a half. So this is case 1 here. Trig function equals a number. This is case 3 here. So I convert the case 3 to case 1 by adding 1 and dividing by 2. Now I've got 2 of these in step 1. Trig function equals a number. I just have to solve both of those. See if I can keep most of that up here. Now you see why I say practice these. You have to just be able to be a little clever on some of them. Sine x equals 0. Here's what we have. Sine x equals 0 or cosine x equals a half. Sine x, oh, I should have used theta. I forgot. I always like to write theta on these so I don't get mixed up with the coordinates on here. But sine is the y coordinate. So if I call this theta instead of x, I would have preferred. Sine theta equals 0. Sine is the x coordinate of the unit, excuse me, the y coordinate of the unit circle. So I put y coordinate equals 0 is this one, right? Here's all the coordinates y equals 0. There's exactly 2 points on the unit circle where the y coordinate is 0. So exactly 2 terminal rays, this one and this one. This one is angle 0, right? So theta equals 0, or theta equals this one, pi. And those are the only solutions in the integral 0 to 2 pi, right? I start here, there's one angle. I go around here, there's another one. I keep going, that's it. I get back to 2 pi, but it's the interval 0 to 2 pi, not including 2 pi, so I can't include the one I get back around. So I just have these two solutions, 0 to 2 pi, not including 2 pi. Or cosine theta is the x coordinate, right? So I can have the x coordinate equal a half. That's the vertical line. Here's all points with x coordinate at half. It intersects the trig on 2 points, leaving exactly 2 possible terminal rays. And if I want solutions only between 0 and 2 pi, I just rotate to here. What's that angle? Well, this side length is a half in the reference triangle, right? 1/2, because it goes to x equals a half. This is 1 because it's a unit circle. Oh, it's a 30, 60, 90 triangle. This is pi over 3. I could say this is the other angle minus pi over 3 by symmetry, but it's not between 0 and 2 pi. Instead, I want to measure it this way. 2 pi, back up pi over 3 and say, oh, it's 2 pi minus pi over 3. Put them over a common denominator. 2 pi is multiply top and bottom by 3 and get 6 pi over 3. That is 2 pi. 6 pi over 3 minus 1 pi over 3 is 5 pi over 3. There's the other angle. So I've actually got 4 solutions here, right? Theta equals 0 pi from that one. And then pi over 3 and 5 pi over 3 from this one. 4 answers in the interval 0 to 2 pi. Another one. Here's there we go. If I look at 7a, sine squared x minus cosine squared x minus sine x equals 0. How do I solve this one? I want to convert it into one of my other cases by hook or by crook. And unfortunately, I've got 2 different trig functions in here. I don't know how to solve it with two different trig functions. I try and reduce it to one trig function. So how can I get it to one trig function, maybe using identity? Whenever you see a square of a trig function, think the Pythagorean identity. We have the Pythagorean identity, sine squared. Let me call this theta again, tell me, get myself in trouble. I recommend changing all these book problems and homework off to theta so they don't get mixed up with this picture here. Sine squared theta plus cosine squared theta equals 1. That's the Pythagorean identity, the first and most important one. If I solve this for cosine squared, by subtracting sine squared from each side, I've got cosine squared is 1 minus sine squared. We'll replace this with parentheses 1 minus sine squared. Now it's going to reduce to just sine theta, one trig function. So I'm going to get one trig function with one angle. That's the object element. The last one had two different angles, so I used a double angle formula to get it out. This one has two different trig functions. I use the Pythagorean identity to get it out. In either case, now I get down to one of those first four cases. So this is sine squared here, minus 1 minus sine squared is minus 1, and if this minus distributes, minus is plus sine squared, minus sine theta equals 0. Minus 1 plus cosine plus sine squared. This is now 2 sine squared minus sine minus 1 equals 0. There it is. A quadratic equation and a trig function. So some of these you need a trig identity to put into the right form. Now this being a quadratic equation and trig function, I can say this is A, minus 1 is B, minus 1 is C. So evidently, if I put x equals sine theta, I get a quadratic equation. 2x squared minus x minus 1 equals 0, for which I can try factoring or I can try the quadratic formula. Which should I use? Might be able to use either one. Let's try factoring just to see if we can do it. Blank x plus blank, blank x plus blank. Quadratic formula will work. It always works. The product of these is the lead coefficient. The product of these is the constant term, the -1. So what can I put? I need a 1 and a 2 here. And these have to be -1. So maybe this is 1 and this is -1. Let's see. Actually, let's try it the other way first, just to try it wrong. 2x squared plus 2x minus x is x minus 1. So I get plus x instead of minus. I've got these backwards. This one needs to be plus and this one needs to be minus, and then it will work. This time this is the 2x squared. This time this is minus 2x and this one is plus x. This time this minus 2x and plus x is minus x. And then this time this is -1. It foils properly. So if you put the right numbers in, this will work. Right, that's a little simpler. 2x plus 1 times x minus 1 equals 0. And these are all equivalent. Means they have the same solution, so they're equivalent equations. The zero product property applies. Either this factor is 0 or this factor is 0. This factor equals 0 says that 2x plus 1 equals 0. This factor equals 0 says x minus 1 equals 0. These are linear equations in the trig functions. All right, so we solve this one by subtracting 1 and dividing by 2. We observe x has to be -1/2. This one, if we just add 1, we get x equals 1. Those are all solutions to this quadratic equation. But wait, x was the sine of theta, right? So this is equivalently sine theta equals -1/2 or sine theta. So now, oh, go to step one, right? Trig function equals a number, trig function equals a number. By step one, we can now solve each of these on the unit circle. The first one is the y coordinate. Sine theta is minus a half. There's all points y equal minus a half. That means 2 points on the unit circle where y is minus a half means exactly 2 terminal rays through them. If we drop the perpendiculars, this side of the triangle is 1/2 because it goes down to y equals minus a half. This is 1, this makes a 30, 60, 90 triangle. This angle must be pi over 6, 30 degrees. And this one also by symmetry. Or we could solve sine theta equals 1. Y coordinate equals 1. Means I go just tangent to the unit circle, right? When you do that, there's only one point of intersection. That's the angle right there. It's the right angle, pi over 2. Evidently, in the interval, I should have put this at the beginning of the problem. I think it's on the instructions. Put, I don't know if you can see here, 0 to 2 pi. Theta between 0 and 2 pi. For theta between 0 and 2 pi, I have exactly 3 answers now. If I want all angles theta, I have to add 2k pi to each of these. I get theta equals 7 pi over 6 for this one, right? Pi plus pi over 6 is 7 pi over 6. I don't want to write minus pi over 6 because it's not in this interval. Instead, I go this way. I have to go to this one, 7 pi over 6. I go to this one, 12 pi over 6 minus pi over 6 is 11 pi over 6. Those are the two from here, and this one is pi over 2. 3 answers for this one. Well, last but not least, certainly, we'll do another one probably next time. The object next time is to try all these things out on the practice problem set and on the sheet of the homework, and bring questions you have, and we'll go over as many as we can in class reviewing for the test. So we said, and I didn't get to this one yet, sometimes you just have to leave in form of inverse trig functions. And this is such a problem. This would be 8a. Suppose I wanted to solve tangent squared theta plus 3 tangent theta minus 3 equals 0. This is actually of the form for a quadratic equation and a trig function. What do we do for that? We put x equal to trig function. So I don't even have to convert this one. It's a little easier like that. X equals tangent theta gives a quadratic equation. X squared plus 3x minus 3 equals 0. The last one I try to factor this, right? This is not so easy. I'm going to go straight to the quadratic formula and say x equals, here's a, b, and c. Minus b is minus 3. Plus or minus square root b squared minus 4 times a times c. All over 2a. We observe since the square root of a positive, there's 2 solutions to the quadratic formula, right? 9 plus 12 is 21. So this is square root of 21. My answers are minus 3 plus or minus the square root of 21 over 2. You know what that means? It means it's a good thing we didn't try and factor. If we would have tried to factor this one, this is what we would have got. We would have said, oh, blank x plus blank x plus blank. This is only faster when it's easy to fill in the blanks. The first ones have to be 1 to give 1x squared. And then what goes in these blanks? It turns out that if you write it this way, if you write ax squared plus bx plus c equals 0, this left side always factors as a on the outside, x and x minus these numbers. And guess what goes in these blanks when you factor? It's those things. minus 3 plus square root 21 over 2, minus 3 minus square root 21 over 2. I could guess all day and never guess to put these in the blanks, right? So factoring is not a good idea on this one. When the quadratic gives whole equation gives whole numbers, then yeah, you could have guessed at the blanks easier probably. But use the quadratic formula when you can't figure out what goes in the blanks, because it may be all day trying to guess, right? So these are the two solutions, but what is x is tangent theta. So I need to find solutions tangent theta equals these two numbers. Now tangent theta equals a number always has a solution, right? Tangent could be any number. Look at this graph. Looks like this, and it repeats. By putting in the right value of x, you can make y as big as you want. So these will both correspond to solutions. What are they? Well, we have two cases. Tangent theta equals minus 3 plus square root 21 over 2. Or we have tangent theta equals minus 3 minus square root 21. Both those give a solution. Tangent can be anything. What's one solution to this? This is a big part of it. One solution is theta equals the arctangent. When you have tangent equals a number, one answer is always the arctangent of that number, whatever it is. That's a solution. Similarly, over here, one solution is the inverse tangent of this one, minus 3 minus square root 20. What are all solutions? What it turns out is that tangent is pi periodic. So this is one solution, and every other solution is just add k pi to it. These are all solutions that make tangent equal this number. It's similarly over here. So we're going to have solutions like that for any value of k pi. But the problem didn't say that. It said solve it in 0 to 2 pi. Make sure I'm about out of time here. Be careful. All right. So what are all the ones that are between 0 and 2 pi? It's wise in this case to draw the unit circle, I think. Square root 21, right? Square root of 16 is 4. Square root of 25 is 5. So this is between 4 and 5. It's 4 point something. This is a positive number. It goes in the first quadrant, right? I don't know exactly where it is, but it's something, maybe it's there. Arctangent minus 3 plus square root 21 over 2. How about this one? Oh, and then the other one, you can add pi to that. This one would be arctangent minus 3 plus square root 21 over 2. Those are exact answers. And this one's in the first quadrant, so it's between 0 and 2 pi. This one you added pi, it's in the third quadrant, it's between 0 and 2 pi. So two exact solutions in terms of inverse trig functions are arctangent minus 3 plus root 21 over 2, and the same plus pi. There are two solutions, they come out of this one. Any other solutions, if I add k equals 2, I get 2 pi plus a positive number, it's too big. If I put k negative, I get a negative angle, it's too small. So only k equals 0 and k equals 1 in the first equation. Give something between 0 and 2 pi. Now in the second equation, this one actually is a negative number, right? This is negative. Negative and negative. Arctangent of a negative, remember arctangent between minus pi over 2 and pi over 2. If you're taking arctangent of a positive number, you get something in the first quadrant. But arctangent of a negative will give you something in the fourth quadrant. So something down here is going to be this arctangent. Minus 3 minus square root 21 over 2. It's going to be in quadrant 4. That's not between 0 and 2 pi. Right? So what are my angles going to be? I'll draw this one a different color. I don't use that one. Instead, I add pi to it. That'll put me in the second quadrant. And I say one solution is this one plus pi. It'll put me between 0 and 2 pi. And then I add 2 pi to it. So instead of getting this angle going this way, I get this angle plus 2 pi is this angle. So arc tangent, that's k equals 1 and k equals 2 in the second equation. Told you it's a very tricky section, right? Minus 3 minus square root 21 over 2 plus 2 pi. This is negative, so this sum will be between 0 and 2 pi. K equals 3 is too big, k equals negative 1 is negative, that's it. There are 4 solutions. These are the exact solutions. I say you can write the exact solutions in terms of inverse trig function. I'm out of time, but we'll say you simply use your calculator to get rounded answers because the problem also asks you to round. But you just put these numbers in. Make sure it's in radians mode. If it's in degrees mode, you get degrees here and add it to a measure of radians, you get the wrong answer. So get the arctangent radians. Unless you put 180 here, then you can do this in degrees, and this was 180. So arctangent for a rounded answer. I already wrote the homework, just do all the problems out of that section, but as you can see, they're kind of long. If you see how to do one, you might just skip over it. All right, thanks for coming in today. That's all.